Okay, I'm gonna try and see if I can get my video and if I can get my face and the iPad screen on at the same time. Um, we'll see how that goes though. So, hey to everyone who's watching on YouTube. Apparently do not disturb does not work exactly how I think it works. Let's see if we can fix that actually. Okay, well, now it's just my face now. Okay, so it does. Okay, I gotta mute myself because now I'm coming through on YouTube. Sorry for this. Let's go look at my iPad settings to figure out. Do not disturb, silences calls and notifications. Yeah, don't. Notifications. Never. Hello, yes. I am an engineer and I am figuring out technology, like how an iPad works and why I can't share my iPad screen with my Linux computer for capture without having an external capture device is beyond me. But yeah. All right, let's try starting a broadcast again and do. All right, let's get started. All right, I'm pulling up chat. So this is going to be a little bit different than some of the other stream stuff that I've done, where I'm usually working on code or I'm working on Q&A or something like that. For this one, I've had a couple questions, or I've been doing some work with my library BBQueue lately, and I've had some questions about how it works. So me and Andrea, when we came up with what the algorithm behind BBQueue, we wrote up a big post about it. So I'll definitely link to that, but you should read that if you haven't had a chance. But that's more about like how the algorithm itself works. More, I kind of wanted to draw up some new diagrams for like a blog post that's kind of a practical usage guide of how to use BBQueue and a little bit of how it works under the hood, but mostly just to kind of understand how it works. So I'm going to be that's why I'm sharing my screen, and unfortunately it's only 720p, so what are you going to do? It looks kind of silly on my screen. It looks better with a white background than a black background. The compression really did not like that, but I'm going to draw a couple diagrams about what BBQueue is and how it works. And I am keeping an eye on the YouTube chat and the Matrix chat. So if you're in either of those, feel free to ping out with questions, and I'll do my best to answer those. Please do answer questions, or please do ask questions, because yeah, I'm gonna end up writing a blog post of this, like a written version of this. So I'm probably gonna watch myself talk a bunch, and turn that into the actual notes for my blog post, and then put it up in a blog post for people who don't like watching videos. And then probably also update the docs for BBQueue as well. So if you do have any questions, feel free to say hi, or just wave, and I'll keep an eye on it. All right, yell at me if my audio is not great. Apparently my mic has been flipped for some amount of time, so I flipped it back around. So we'll see if it sounds different. Okay, so let's get started. We're talking about, let me move the mic more in front of my face because I'm going to be looking over here. So we're talking about my library BBQueue. I can't write. So you also have to deal with my terrible handwriting until I type this up. But what it is it is a circular buffer. Buffer. It's inspired by a library called Bitbuffers by Bitbuffers, which are actually they're nuts. I don't know how old they are. I'm sure it's based on a paper from like 1981 or something like that. But I see that them fairly widely used for things like audio processing and things like that, where you do have like DMA in the loop. So it's also, I should space these out. Because I'm writing with the chunky pen. It's meant to be DMA friendly. So the idea here is that unlike a regular circular buffer where you have kind of one producer and one consumer, where both of those are software components. The idea for both bit buffers and BBQ is to be friendly to DMA. So DMA is direct memory access, which means usually you have a chunk of memory and you point your hardware and you say, hey, memory starts here and there's 128 bytes. Go copy it yourself. And it can either copy from like memory to memory, or more often it copies from memory to some peripheral. Like if you have a serial port or an SPI port or something like that. Instead of like putting 1 byte at a time in the hardware, you might just say, hey, hardware, here's 128 bytes. Let me know when you're done. And that way your CPU doesn't have to sit there and keep shoving bytes in it, which wastes a lot of time. I talk about this in the original post. It's something like if you have a 64 megahertz processor like a microcontroller might have, and if you're sending data on a serial port at 115 200 baud, it's something like 22,000 times slower to send the bytes than to just copy the bytes if you were copying them in a big slice. So it can end up being sorry, this is BIP buffers, BIPBUFFERS, BIP buffers, bipartite buffers. And they're called that. Well, I'll get into that in a little bit, why they're called that and how they work. So yeah, I think that's okay. My implementation is also single producer, single consumer. They are thread safe, or it is thread safe, which means you could have two completely different threads, one doing the producing and one doing the consuming. Or in the case of embedded, you can have your main application be either the producer and the consumer, or and then you can have an interrupt or another task or another thread being the other half, being the consumer or being the producer. This way you can use this on desktop as well with multiple threads. I do use that in some of my tests. But really BBQ was designed to be an embedded friendly crate. Yeah, and that's the other thing is I should probably say it is no STD. So does not require the standard library. It is very friendly for I think most people who are no standard are either embedded or something like WASM, or if you're actually doing operating system development in Rust, that would work too. Yeah, okay, I'm scrolling down so I can actually, let me pop out the chat window. Pop out chat. So that's BBQ. Let's look at a couple other things just to get some basics. So it uses a technique called circular buffers. So this is really common in embedded, where you don't have a heap. So all of your memory needs to be statically allocated, or at least have a known fixed size, where you want to be able to put a variable number of things in some kind of queue or something like that. But you don't want to use a heap and you don't have like infinite memory to use. Um, yeah, those kind of things. I don't know why Zoom is giving me a notification. Now it's giving me no previews. Okay, well, I hope it wasn't important. I'm not seeing anything on up here. Okay, well, so typically what happens with a circular buffer is you would have something like um, you'd have a linear chunk of memory, and this would be chopped up into chunks. So I'm going to draw some linear memory chopped up into chunks. Oh, look, it was an order of 2. Wonderful. So we're going to have like position 0, 1, 2, 3, 4, 6, 7, 8. Let's just call it at 8, actually, because that's going to be easier to draw. Okay. So we have a circular buffer with 8 slots in it. And so this might be, it depends on what you're using this for, but I'm just going to say these are just bytes. And these are in some linear space in memory in there. So you have a circular buffer of 8 bytes. And normally what happens is you have, let's get some more colors going here. Um, so you'd probably have something like so the way this normally gets implemented is you'll have a read pointer and you'll have a write pointer. And when you want to push something in here, you will, when you're writing some data, like I want to write 27, you'll put the data where the right pointer says, and then you'll move the right pointer over one. So you go, this is where I'm going to write next, and this is where I'm going to read next. And usually you have some check in your library, depending on how you implemented it, that like once the read pointer equals the right pointer, you can't read anymore. So once they're touching, that means that you've hit like the end. So if I were to go and write like, um, you know, 30, let's just 50, 60, 70. So I've done, let's see, 8 pushes. Oh, I guess this should be 0 through 7 if I'm doing this correctly. So 0 through 7. So I've done 8 pushes here. So, and when I'm done with this, then the right pointer is going to be actually back around here. So it's actually going to be back at 0 again. And the right pointer knows, hey, well, actually, usually when you implement this, you are not allowed to make I don't know. There's a bunch of different ways to implement circular buffers. So I'm just going to do the simple case because I'm not explaining general circular buffers today. I would recommend reading them. They're one of the libraries that I see. So I do a lot of like software consulting. Um, it's always awesome to go see someone's home written circular buffer library for the first time because they're really simple, but they're really easy to get wrong in like a bunch of different ways, particularly if you're trying to make them thread safe and stuff like that. So I've definitely walked into companies before and found like 4 different implementations of a circular buffer, and all of them had different bugs, which was awesome to see. So I won't go too much into circular buffers now, but the real core component here is that they're like a big linear chunk of memory. So I've written 7 things, so then I can go ahead and if I were to read, I could pop them one at a time, and I would get 27, then 10, then 20, then 30, then 40, then 50, then 60, and then I'd have nothing. I'd have drained the entire buffer. So at that point, I will have moved my read pointer up to here, and that means that there is no more data to be read. Um, but then when I want to go and write the next thing, so let's say I've gone ahead and consumed all this data. Um, then what I'm going to do, if I wanted to write 2 more pieces of data, I would write 70. And now that this first one is freed, I should actually probably erase it because it's available. Then my right pointer, and the reason they're called circular buffers is after you get to the end, you just wrap back around to the beginning and then you start writing the next chunk of data. And your library should be smart enough that it handles this elegantly, and then when your read pointer comes around, then the next time you go to read, you're going to read 70, then 80. So you're just going to kind of walk through, and the space just goes kind of around and back and around and back, kind of over and over and over again. So it feels like you have this like infinite queue of data to store things in, as long as you never have more than 8 items in the queue at any time. So these circular buffers work really well, and it's pretty direct to make you can make a thread safe one. So for example, if you have something like in the heapless crate, heapless has SPSC colon Q. And that's basically what I'm describing here. Um, this is kind of like a very traditional ring buffer or circular buffer. They have a bunch of names, but you'll see these all over the place. They're used sometimes even hardware understands these and has ways of handling this, but usually you have like your chunk of memory, you have a read pointer, and you have a write pointer, and those move around, and there's certain rules about when they can touch and when they cannot touch and what that means to be empty or full. Some circular buffers even let you overwrite the oldest data. So like if you run out of space, instead of just saying, oh, you can't put anything more in here, you'll overwrite old data, which is sometimes okay if you're doing things like continuous sampling of some ADC or something like that. But Yeah, it all depends, and there's a bunch of different libraries, and they're easy to get wrong. Heapless SPSCQ in Rust is super good, and I use it a lot of the time. But the problem here is that whenever I'm doing these core actions, so either this is the wrong color. Either if I'm writing, then I'm going to be pushing, and if I'm reading, I'm going to be popping. So at least in Rust, you usually represent that as a single function call. So you're saying, I'm pushing 1 byte, I am popping 1 byte. And usually because the way that you implement these to be thread safe, it's important that you do one thing at a time, because then it's like an atomic operation. And that makes it thread safe, because you don't have like, oops, I moved the pointer, but there wasn't valid data there. So someone could have read corrupted data. Or I accidentally updated the pointer, and now like I looped over like the pointers crossed each other and it caused a problem or something like that. So this works. So someone's asking, these are slots in RAM. So usually this is just a chunk of memory. So it's in RAM typically, yes. It's not necessarily like a page or something like that of memory. Usually it's just one continuous region of memory. So this would be literally 8 bytes in a row. A lot of times you make them much larger, like a kilobyte of data in there. But with your traditional circular buffer, you're addressing each item at a time. Heapless SVSC queue can do bytes at a time, but it can also do structs at a time. So these 7 elements or these 8 elements, instead of being bytes, they can be structs, which is super handy, particularly if you have a fixed size structure that you're going for. But yeah, the two downsides here is that these push and pop items are you're doing one whole item at a time, whether that's a byte or a struct. Doesn't really matter for SPSCQ. But if you are doing this in Heapless SPSCQ, if you have a variable size message, or even just a stream of bytes, like let's say you were receiving data on a serial port and you just wanted to like keep reading in from the serial port, and there's no real like start or end or anything like that. You need to send like a variable size data or a stream of data. So you totally could use a heapless SPSC queue of bytes, but you'd have to manually push each byte into that circular buffer, which works, but it's maybe slower than you want. And it also means you can't offload that to the hardware. Um, so yeah, the kind of let me what we don't like for circular buffers. So this is what I didn't like about traditional circular buffers is that you had to do one item at a time, which means that no hardware offloading, like because you have to push each item at a time. Um, you can't really like just give a chunk of data to your hardware to say go fill this up, because you have to be very careful about how you insert the items or pop the items or anything like that. I'm realizing my handwriting, on top of being pretty bad, pixelated, it's even worse. So I'll try and be more careful. So it has to be one item at a time, which means no hardware offload. Um, Also, it generally means that each slot has to be um, has to be same sized. So what I mean by that, so in this case where there are bytes, each thing that I push in there has to be a byte. Like if my type of each item in this ring are bytes, then I have to put 1 byte in at a time. If I'm pushing structs in here, like let's say I have some struct with like 5 integers in it, then each of those slots have to be the same size, which is sometimes okay, but sometimes you have like variable length messages or something like that. So you might be receiving packets. So variable, when I'm talking about variable data, imagine you have a packet. My handwriting is awful. You have a packet from a radio. So let's say you're receiving packets off of a radio. One packet might be like 120 bytes, and another packet might be 20 bytes. So if you had a circular buffer of bytes, you could put them in one byte at a time, and that's fine. But if you said, oh, okay, well, 120 bytes is my biggest message, so I'm just going to make a struct, or even just a a U8 120 or something like that, just an array. But the problem is everything you put in there has to be of the same size, which means if you only put 20 bytes in there, then you've got this other 100 bytes that you're not doing anything with, which is kind of wasteful. And so sometimes you have like always the same size messages, or you're not trying to offload things to hardware. In that case, like a heapless SPSC queue will work really well for you. But if you are using something that's more like a stream, like I have a literally was designed for like a serial port in and out, like to have the hardware just manage the data coming in and the data coming out, or something variable, like you have a bunch of packets that are differently sized, and there's a big difference between the smallest packet and the biggest packet. Yeah. Someone is saying, is it possible to do a circular buffer of pointers and encode the type it points to in the lower bits of the pointer tagging? You probably certainly could. I'm sure anything is possible. I haven't played around with a good library in Rust that does that. And also pointer tagging uh, has some ups and downs to it. Means you can't do it safely in Rust. There's probably some tricks you could do. So certainly you could do pointer tagging, but I'm going to leave this just between BBQ and traditional circular buffers for right now, just because that's what I'm explaining today. But good question, Carlos. Um, so what does BBQ do instead? So BBQ, um, I guess maybe I should explain bit buffer queues first a little bit. I'm not going to go too deep into it. Let's say um, a bit buffer still uses a linear chunk of memory. Let's get a nice clean rectangle. So a bit buffer still uses a linear chunk of memory, like our circular buffer, and it does generally kind of, when you hit the end, you wrap around and go. When you hit the end, you wrap around and you go back to the beginning, and that's kind of your circle goes over and over again. But what BIP buffers does is it lets you have um, at least two chunks of the data at a time. So you can always have like an A side and a B side. So you might say like, okay, I have my A side, and I can write some data in here. And then when I'm done with it, I can commit it so it's ready to be used again. Um, and then someone can go through here and, so someone's written all this data, and then our reader comes through and consumes all the data. So you go, okay, cool. Now I need my next grant. So all of this is freed up. So this is no longer being used anymore. You go, okay, cool. I've used up all that data. And then you do another one where you say, okay, I need to fill some more data in. Okay, so now this is in here, but now I want another big chunk of data. So to do that, you end up making a B region, where you say like, okay, I still have that right pointer and the read pointer here, like I had from my regular circular buffers, but I actually have two sets of tracking variables. I've got the A side tracking variables and the B side tracking variables. So in A side, and I know I'm using red and blue for both A side and B side, and also reader and writer, but the trick is that you have like the circular buffer can keep track of two regions at the same time, and it does that so you can have um, multiple grants out at the same time. You can work with them, um, and the idea, at least with bit buffers, is that like once A is done and only B exists again, so like once you're done with this, then you just do a seamless swap and um, oops, and this becomes A, and then whenever you want to make the next one, you can make B. So basically, you can always have like two things going at the same time. The C++ implementation that I found, like if you Google bit buffers, there's a blog post that goes to a C++ implementation. I don't think it's actually multi-threaded safe. It does look okay if you have a single thread and you are only working with that. But when I was kind of auditing the C++, and I will admit my C++ is not perfect, so I could be missing something. But it looked like that swap, like the atomic swap with A and B, um, didn't look super thread safe, which is why kind of Andrea and I came along and that. So this is a little different from a double buffer. So someone mentioned a double buffer where you have actually two completely separate regions. And then you kind of are always swapping in between which one's the active one that you write into and which one. So this is supposed to be sort of like bit buffers, and this is kind of like double or ping pong buffers. So they're slightly different in that bit buffers still let you have like variable size chunks in here. So you can kind of have like the nice things of double buffering where you have two buffers where one's kind of always free, but the nice thing of circular buffers where you have variable amounts of like how big A and how big B is. Um, like I said, I would recommend reading the blog post for BIP buffers because it's actually a really well written blog post. But we wanted something slightly different that was also a little easier um, to make sure was thread safe, at least for a single producer and a single consumer. Um, so this is kind of history. Like I said, read the blog post for bit buffers. There's a good one for that. There's a lot of written material out there, good and bad, for circular buffers or ring buffers. I don't want to go into that too much, but I did want to explain sort of some of the history. And why you wouldn't want to use just ping pong buffers is also similar. One, you're limited to the number of slots you have. And two, if you put, if you have 120 byte ping pong buffers and one of them's full with all 120, that's great. But then in the other message, if you only put 20, you've got kind of all this wasted space in here, which space is sort of a premium for embedded systems. So anytime we can avoid unnecessarily wasting space, we like to. Okay, so that was a lot of stuff that isn't BBQ. Let me go actually into BBQ. Okay, and um, I'm going to kind of split this page in half because I mentioned that BBQ is a single producer, single consumer. Um, so the easiest way to actually think about this is by breaking BBQ up into the different parts that it can operate in. So we've got our producer and we've got our consumer. And basically each of these has two things that it can do. And producer means they're the one that's shoving stuff into the BBQ, and the consumer is things that are pulling out. So like this is kind of the push, if we're using the word from the circular buffer, and this is the one that pops. So we've got the pusher and the popper. And like I said, this is at least in BBQ, it's a single producer, single consumer. So you can only have one producer and one consumer. But the trade-off there means that you can have them in different threads. So you can have one producer in one thread and one consumer in another thread, or one of them can be hardware. So the actions, the producer can get a grant. The touchscreen feels too slow to keep up with human writing speed. I don't think it's just my handwriting. Well, thank you. That's fair. But also my handwriting is terrible. I can show you some paper notebooks too. But yeah. So the producer can get a grant or well, I'll get back to that. And then it can commit. And a consumer can read and it can release. So these are the four actions, and like these two are sort of similar to each other, and these two are sort of similar to each other. So what a grant is means give me space to write bytes. So the grant says, okay, I've broken off a chunk of data, and here you go. You can have it, and you can write bytes to it. So you might request a grant of 32 bytes or something like that. And it will say, okay, here are your 32 bytes that you requested. I guarantee that these 32 bytes are linear. So they're always in a row. In Rust terms, this means I can have one slice. So like these 32 byte, you will be given a mutable slice to these 32 bytes, which means all of them are continuous in memory. They're also yours until you're done with it. So at this point, you could do whatever you want for as long as you like with that grant until you mark that grant as done. And that's kind of the other side. Whenever you're done writing those 32 bytes, then you commit. So commit means make available to read. So even if you requested a grant of 32 bytes, the consumer can't see that data yet. It's still yours. You, as the producer, are still playing with those 32 bytes. So it can't have access to it until you committed it. But once you commit it, you lose access to those bytes, and they go off to the other half. It goes to the receiver. Basically, it's been sent. Once you commit, then the data is available to read on the other side of the buffer. So read says, give me available bytes to read. And again, you might say, okay, break me off the available readable bytes. So if you just did that commit, it will say, oh, wonderful. We have 32 bytes that have just been committed. Here, you can have them. And once the consumer has those 32 bytes, and again, they're guaranteed to be continuous, which means I get an immutable slice, a read-only slice of those 32 bytes, and I can do whatever I want with them for as long as I want. It's only read-only access, so I can't write to it, but I can read from that and like look around from it as much as I want for as long as I want until I release it. And once I'm done reading these bytes, I say, okay, I'm done with these 32 bytes. They can be recycled now. So releasing means make available to write. So this frees up the space in the buffer again to be written on. So if the producer totally filled up the buffer, then the next time it asks for a grant, the BBQ will say, nope, there's literally no bytes I can give you right now. Sorry. Until the consumer has gone and released some of those bytes. And once you've released them, then they're available for the producer to use for its next write grant. Okay, so let me so this is kind of the 4-part life cycle. So I mean, like if you were doing this totally linearly, this would be step 1, step 2, step 3, and step 4. But because these can be happening in separate threads, 1 and 2 and 3 and 4 can be happening totally out of sync with each other. It doesn't have to be in order, but yeah, it could be totally out of sync with each other. One can be in an interrupt, doesn't really matter. So I'm going to draw this in a second, but I need some water. Okay. So real quick, let me make sure I don't have. Okay. Just checking chat. Okay. So how does this look for BBQ? I feel like I need a big. This is my big linear section of memory. And then I'm going to need a couple colors, or I need to come up with a scheme. So we start. Let's just start with. I'm not going to draw the pointers in here or anything yet. I'm going to give the really high level, overview of this. Okay, so what color did I use? Red for producer. Okay, so what probably will happen linearly? Let's say this is a total of 128. I'm in shape drawing mode. 128 bytes. So let's say the whole chunk of memory that I have is 128 bytes. So let's see. So that would be 64, 32. So 32 would be about a quarter of it. So let's say I started by doing a grant and I request 32 bytes. So like that's step one. So I'm gonna take roughly a quarter. Okay. So right now, um, we've got this granted, which means you can kind of think of this as being locked. So you actually receive back a Rust structure called a grant that represents your ownership of these 32 bytes. No one can do, so this is 32 bytes. So you have the ability to do it, and you've got a slice that literally is these continuous chunks in memory. And you could do whatever you want with it. You can mem copy into the buffer. You can like set each byte in whatever order you'd like. The other thing that you can do is because this is a slice, you can get a pointer that points here. Um, and you can hand that pointer to your DMA engine and just say, hey, start here, go for 32 bytes, and give me an interrupt back when you filled it. So, like, if you were using DMA on the producer, this would be something like you're receiving data from a serial port. Like, you're expecting to be given data. So what you might do is go, okay, I will set up a grant of 32 bytes. Uh, Serial port hardware, fill this automatically. Let me know when you filled 32 bytes into here, and then you just leave your interrupt or something like that. And because your grant is still there, this data is reserved and no one else can touch it. So you would wait until this is done, and then you would, when it is all done, you will, I guess it's called commit. You will commit. Now, technically, BBQ lets you commit smaller than your total grant. Let's say you got the end of the serial message and you'd only receive 16 bytes. You could decide to just commit the 16 bytes. You can commit however you want. It always starts from the beginning. Let's just say for now we commit 32 bytes. So that what that does is you have to give back your grant. You actually have to return the grant. And doing that, let me check something real quick. Sorry. Yeah. So when you give back the grant, so you actually give it back, like you have to commit, which consumes the object in Rust. What that does is it goes, okay, this grant is no longer active, and it means that we can now read anything in this range. So we can now read up to here. And it's no longer writable. So really, actually, the read pointer was already there. Let me draw some pointers because I said I wasn't going to, but now I'm going to. So read was always here. But then once we commit, the right pointer moves up, and then our consumer half says, oh, wonderful, we have some committed bytes. So I'm going to draw kind of a line here, and I'm going to cross hatch it. And the cross hatch means that this has been committed. So it's not pending anymore, it's written. Hopefully this is all making sense. Feel free to shout out in the chat if you are not sure. Okay, so then what I might do is on 3, I might read. And what BBQ does when you say read, you don't actually tell it how many bytes you want to read. It just gives you the next chunk of bytes. So now what we have is we have um, this chunk of data now has a like a read lock on it. Basically, this chunk of data has an active read grant on it. So again, here, if I was, let's say, I was receiving on one serial port and I wanted to immediately send out to another serial port, I could tell my DMA engine, I could say, hey, I've got this same pointer here, this same start pointer, and please send this data on serial port number 2 or something like that. Or if it's a loopback, I could just send it on the serial port. So this pattern can kind of go on and on. So I could have another write grant for 32 bytes, and then I could commit it, and then I could have another write grant for 32 bytes, and then I could commit it. And let's say I have one final write grant for 32 bytes, and then I commit it. So now I've used up the entire queue. I'm waiting down here at the end. Let's say we'll go ahead and release. So the reader keeps polling. So someone asked, what happens if I try and read a non-committed slice? Do I get an error? I should actually show you so these are each Rust functions that return a result. And they will all return an error at least, okay, grant and read, return a result. And if there is data to be given to you, then it will return an okay. And if you say, give me a grant and there's not one available, or I want to read the available and there's no data available, it will return an error. So you can't like get access to the wrong data or handle it wrong. You'll just get a result that is an error. So Rust won't let it happen. Same with commit. If you try and commit or release more than the grant than you have, then it will just cap it at what you were given. Yeah. So there's actually really no room to hold it wrong, because if you hold it wrong, then your code just won't compile. So yeah, as a reader, you would have to keep polling to see if that was available. So you'd have to keep looping or waiting until there was more data available before it would give you back the next grant. But let's say I've read this and then I've actually gone ahead and released it. So where we are right now, our reader has read the first 32 bytes, and our producer has written all 128 bytes, 32 bytes at a time. So it's done like 4 DMA transactions or something like that, and it's decided, hey, I filled this up. So right now, if it tried to get another grant, before I released that, it would say, nope, there is no more data to be have. The buffer is full. But what happens when you release this, then we come back here and we actually clear all this out. We say, okay, this has been released. And oops, I'm blowing up my walls here. Yeah, so because I've released it, once I've done the release, this data is now available again. So now, and let me get rid of these locks because they're not there or confusing anymore. Now basically, if I wanted to get a new grant, I could come over here and, this is now available. The writer is smart enough to say, hey, there's no more room at the end. Is there room at the beginning? Oh, yes, there is room at the beginning. So I will begin giving you data over here. And now you have a grant here. So now you have this lock on data until you're done with it. So, and then at some point, the reader could go through, and actually the next time you call read, it will give you all of the data. So instead of just getting the 32 byte chunk, the next one you get like 96 bytes. So you get a read slice of 96. So let's say you get a read slice of 96. So this is actually all in your read grant right now. and you process like half of that. You say, okay, well, I've chewed through 48 bytes. I need to think a little bit longer before I do anything there. So you maybe got a grant on this, but then you only release up to here. So BBQ will let you do that. When you release it, you tell it how many bytes to release. So if you just said, I'm going to release 48 bytes, then it will go, okay, cool. Well, I will keep that other stuff ready to read. And we'll go ahead and mark this as ready to be used again. And then you delete your lock. And then later, if the right grant wanted to come along and write some more stuff, it would be able to. But yeah, so it basically just goes round and round and round like this. Basically, like you keep pushing forward until you hit the end, then you go all the way to the back, and that works really well actually. So this is kind of like the basics. You just like push stuff and pop stuff, and it goes round and round and round, and it works really well. What I didn't show is what happens if you request data that is not available. So let me explain what I mean by that. So before I always said I'm requesting 32 bytes or something like that. And that worked out really well because we had that space available. So let's say we have 128 bytes again. And let's say we've read and written a couple times. And we have, let's see, what am I using for colors? Let's say we're at the point where we've read up to here, basically, and we've written up to here. So, we've gone through, we've written to this data, we've committed it. So this data is being used. We've cleared out. So this is maybe like, we've got like 32 bytes that's totally free and ready to be used here. And then maybe we've got, I guess that would be something like 60. I have an eraser. What am I doing? Something like 64. And then let's say we have like 22 bytes that are used. So these are free. This is used, waiting to be read. And this is free. We've got 10 more bytes. I can't do math. I guess this is actually, let's just say like, I keep wanting to go to, it's 64 big. Let's say 50 have been used and we've got 14 free. So now it actually does add up to 100. Yeah, so someone's actually asking what if a grant or a read wraps around? So I'm going to go over what happens when the producer wraps. So let's say we're here. We've got 64 free at the start over here. We've got 64 bytes free over here. We've got 50 that are used and are waiting to be read. And we've got 14 free. Well, what happens if the producer comes along and it says grant 32? It says, I want 32 continuous bytes right now. Well, we don't have 32 bytes at the end. We do have 32 bytes available at the beginning, but how do we handle this correctly? Well, what happens is there's actually one other kind of pointer, and we call this the watermark in BBQ. So what the producer says is there is not room at the end anymore, so I'm going to have to jump to the beginning. So what it does is it puts a big old mark right here. It basically draws its own wall here called the watermark that says, I'm artificially ending BBQ here. Like, yes, we are wasting, or we are unfortunately wasting this space, but hey, we guaranteed that we'd always give you continuous memory regions. So then what it will do, it'll automatically jump the right pointer back here. It'll break off that 32 byte chunk that it gave you. And then this now is the chunk that it gives you. It says, okay, this is now your write grant. And actually, no one other than BBQ itself is aware that we've terminated the circular buffer a little bit early. We've said, okay, so then normal operation resumes again. Our right pointer is over there until we come through and we read all of this. And the next time we're given a read grant, we'll get a read grant for this whole region because BBQ is smart enough to not give you a read grant past the watermark. And this is thread safe, by the way, because before there was, well, I'll get into the thread safety later. It is thread safe. I'll explain a little bit more later. But right now, you put down that watermark, and the next time you ask for a read grant, the read grant says, okay, I can read from here to the end of the BBQ, whether that's the real end or the watermark end. Because we got the watermark end, this is now your read grant. It's this big until you go along and, okay, I've released my read grant. It's done. And then we go, okay, hey, we just gave away the last read data. And when we did that, we hit the watermark. Basically, the read pointer hit the watermark. And when it does that, BBQ goes, time to clean up. And what it does is it then gets rid of the watermark. We go back to the real end of the buffer. And then the read pointer loops back around here. And yeah, like I said, the watermark then goes away and we committed our read grant. So basically you can go round and round and round and do that. And if your writer ever hits the end early, and then what it'll do is it'll put down a pin, a watermark, and it'll say, okay, I'm going back to the beginning. And it goes back to the beginning and tries to give you that space there. If there's no space at the beginning, then it says, nope, there's really nothing. But if there is space at the beginning and there isn't space at the end, then it will give you that space. The waste is possibly, there could be some waste. In this case, we wasted 14 bytes. Technically, the most waste you can ever have is the size of the grant that you make. So if there are like, what I mean by that is if there were only 120 bytes, well, I don't know, I probably wouldn't do that. If there were like 40 bytes available and you requested 41 bytes, then you'd be wasting 40 bytes at the end because it would jump back to the beginning to try and give you that space. But okay, so that's the case when the producer wraps. Someone was asking what happens with the reader wraps. So let's say we've got a situation where, oh, that's not right. We've got a situation. We're gonna have another one of our friendly 128 byte buffers. Let's say we've gotten to the place where we've written all of this data. And actually, our producer already went around and started writing at the beginning already. So it's already said, oh, I'm out of space. I need to jump back to the beginning. So our producer is currently sitting somewhere here. And our reader is sitting here. And actually, we've gone ahead and committed all of this. So all of this is totally ready to read. It hasn't been read yet. And our reader is just patiently waiting for someone to ask for a read grant. So I go, okay, I want a read grant. Now remember, the guarantees of BBQ is that anytime you get a grant, either a read or a write grant, it has to be a continuous section. So the next continuous section that it can give you is this. So you've got a read grant. This sticks, your grant lock on it. So you have a read lock on this. But yeah, you are not getting all of the available data. You are only getting the next continuous data. And this is because if it did wrap around, there's no way to like DMA that away. You'd have to do it as two transactions anyway, where you had one that started, let's use a different color. You'd have one that started here and one that started here. So what BBQ says is, well, you're just going to have to ask twice. So yeah, you would do one transaction, you would, let's get my same color blue. You'd go through and you'd read whatever data you want to read out of there. And then when you go and you release that data, um, you would release all of this data. And then technically you could immediately come back and request the next read. And then you would be given this. I do actually have a pull request open where I have some design thoughts about how to get, I called it a split grant, where if this were the case, like what I draw on the screen, you actually would have gotten, you could either get 0, 1, or 2 grants back. Like if only this data over here was available, well, if there was no data available, then you'd get, no data available. If you got 1 grant back, you'd have like 1 region, and then if you got 2, you could have 2 regions. Where this would let you at least get both of these grants at the same time. I haven't taken the time to figure out how to do that safely, or if that's actually like an interface that people want. It's probably possible, but yeah, usually what I do when I'm doing this is I either serve one thing at a time, or usually like I'll do a read, start the DMA, and then when the DMA is done, I come back, release that, see if there's another one available. And if there's another one available, then I start a new DMA transaction immediately. So you can do this pretty seamlessly. But yeah, there's no built in way that you do that. So I think that covers the majority of, I know I've kind of erased this, so I'm going to have to go back and watch my own video and like redraw each of the diagrams in the different states of this. But this covers like the basic operations. So you've got just like normal operation where you're just like pushing and popping from the buffer, and it acts a lot like a regular circular buffer, except for you always have continuous regions and stuff like that. We have the case where the producer wraps around and it goes from that. And then we've got the case where the, what is this? This is the reader wraps. So Olympia is saying at the point where you have to deal with 2 disjoint regions, it starts getting pretty close to just a normal ring buffer. Well, technically, but yeah, in these cases where you do have 2 separate ones, um it's the numbers I'm drawing here are pretty small. Usually when I'm using one of these, I have these buffers be something like a kilobyte or 4 kilobytes or something like that, like a fairly hefty chunk of RAM. And often I'm doing like 128, 256 bytes at a time or something like that. So sometimes you might just have like a little bit of wastage at the end. But honestly, the size of the waste is more or less limited to the largest grant you have. So kind of like before where I said you had the like circular buffer or like a pool of 120 byte chunks, you could technically be wasting 90% in each slot in the pool. Whereas with a BBQ, the most you could ever waste is the size of 1 grant, your one largest grant. So if one of them is like 120 bytes, you can never waste more than 120 bytes. So if you have a whole buffer of like 4K, you'll never waste more than 120 bytes ever. Because otherwise you'd be able to slot that message in, or it would wrap around at a smaller point. So like, yeah, BBQ is not great when you have like a really small BBQ. Like I probably wouldn't actually recommend you make BBQ with like a 64 or 128 buffer most of the time. Usually just having like a regular circular buffer would probably be better. But if you have like a kilobyte or 4 kilobytes or something like that, or even 100 kilobytes of data to store in like a circular buffer or a sync or something like that, then BBQ actually is way, way, way lower overhead. Um, Also, I'm not going to bring up the code because I mostly am drawing stuff today. The code to do these like commits is fairly straightforward if you have atomic operations. So everything except for like a Cortex M0 or M0 plus. Then basically to do each of these operations is like a couple additions and subtractions, like you just do a compare and swap. If you are on a Cortex M0, there's like one instruction in each of these actions, like commit, release, whatever, where you need to take a tiny little critical section just so you can swap two variables to make sure that like your reader and writer never cross each other, basically. So that you never have like one, basically BBQ never gets confused or anything like that. So the overhead's actually really low. I know on my desktop, I've been able to get it to 18 gigabytes a second of transfer. That's pretty silly because it's just sitting in like the L3 cache or the L2 cache or something like that. So it's basically limited by how fast I can copy memory in my RAM. But you can get really silly fast. There's very little overhead here. But yeah, BBQ does really well on streams of data, like I said, a bunch of streams. We also added the ability to do what are called framed messages. So I'll do one little note about how framed messages work, just because I'm in a drawing mood and I don't have this didn't used to exist. So before, what I've drawn is kind of how BBQ has always operated. You just have like a linear stretch, and even if like this was, oh, even if this was like four separate write grants. So like I pushed 16 bytes, then 16 bytes, then 16 bytes, then 16 bytes. The next time I go to read that, I'm going to get all 32 or all 64 bytes back, because normally BBQ doesn't, like, it just thinks of the data that it holds as oh, I got a question. Well, let me finish this sentence. It just thinks of the data that it holds as like linear memory regions. So it just breaks off what you ask it to. I'll get into framed operation in a little bit, but Jan is asking, if you do a read, is it possible to specify a minimum and a maximum size? Or how do you handle cases where you want to read chunks of some exact size? So no, read will always give you what is available. You can then get the grant back. And if it's too small, you can decide to release it and just not release anything on it. Like you can release 0, which just says, okay, just get rid of my grant, but don't release any of the memory in the circular buffer because I'm waiting for more to come in. Or if you want less, you'll be given a slice of, like, let's say you only want 32, but you're given a slice of 64 bytes. You can just process the 32 bytes at the front and then just release the 32 bytes. And then the next 32 bytes will stay sitting in BBQ until you come back for your next grant. There is no way, like if you were in the part where the reader has wrapped, and let's say you have some committed data here, and this is like 20 bytes, and let's say this was 12 bytes. So here are your 32 bytes. The 32 bytes are ready. But if you go and get a read grant, you're never going to get a read grant of more than 20 because that's the next continuous region. So you can get into some trouble with like reading the exact amount that you need, because you will have to basically, like, if you got yourself in this situation, you'd have to copy those 20 bytes somewhere else, then try and get the next read grant and get the next 12 bytes. And then you go, oh, now I've gotten 32. But if you find yourself needing that kind of behavior, actually, you probably want this framed mode instead. So framed mode is something that was added like this week. Corkin89 finally kind of like nerd sniped me into building it. The internals of how it works are completely the same, except that you always, like, basically it keeps track of chunks. And I know that probably doesn't make a lot of sense, but what you would do is something like, I want a grant of max 128. So let's say this is our or not 128. I want a max grant of 64. And again, this is our 128 byte. So BBQ would gladly go, well, I will I'll give you a grant this big. And actually, I'm going to draw some horizontal lines here. This is 100, or not 128. This is 64. And what it does is it actually adds a header. It's a variable sized header. But it gives you still like a continuous region of 64. So what you would do is you would grant, and let's say we only got 32 bytes. Like we went to receive a packet from the radio. The biggest radio packet is 64 bytes, but we only received a packet with 32 bytes. So we go ahead, we have a write lock on all of this for right now. But what we do is we actually, we split this in half. We do actually fill this up. And then we commit 32. And then what happens is we go, okay, well, this isn't a thing anymore. 32. So we released our grant. So the grant goes away. And what we actually did is we saved ourselves some space for a header. So then what we do is the value of this header is 32. So what this header does is it says, okay, the next 32 bytes are part of one message. So when you go to read this, okay, well let's do another one. So then let's do another grant max 64. So we save ourselves some room for a header. And then we're given another 64 bytes. And let's say we actually commit the full 64. So we fill all this space, and then we write 64 in the header. So let's say we've pushed two messages. We've committed both of them. This is the state of our BBQ right now. So in framed mode, read works a little bit differently. Read in frame mode will always give you one frame. And in this case, this is a frame. So actually what it does is BBQ itself goes and looks at that header and it says, that header says 32, which means take this. And when you're given the read grant, you're given access to just one frame at a time. So you get access to the full 32 byte frame, and you can't choose to give back part of that. You either you just release the frame at that point. Actually, I need to make sure that that's true. But I think that's how I wrote that. BBQ. Helps if I spell docs.rs right. I'm going to look at my own docs because docs are helpful. And even though I wrote this week, it still helps to frame consumer read. You get a frame back. Yeah. Okay. Yeah. There's only release. So basically, you get access to this full 32. So what happens here is you get a 32 byte frame. And then you release. And then you read and you get your 64 byte frame. Then you release. Wraparounds and everything like that work exactly the same. The only difference is there will be a little bit of overhead for like these headers. So these are variably sized headers. So if you're sending 1 to 127 bytes, then your header is 1 byte. Then it's 2 to the 7th, which is 127. 2 to the 7th to 2 to the 14th is 2 bytes. 2 to the 14th to 2 to the 21st. Basically, every 7 bits you add, it adds a header byte. But most people are probably only going to end up ever having 1 or 2 byte headers in there. So there's not a lot of overhead, but there's a little bit of overhead. So you can't put like four 32 byte frames in 128 barbecue. You'd need like 134 or something bytes to do that. But yeah. So Jan, if you're asking how to specify a minimum and maximum size, that probably means that you have like a frame or something that you're looking for. So you probably want to use the framed version of BBQ because that will make sure that like your frames also never wrap around. Like you can never have a frame that's like here and here, because it will just force the wrap to happen. So it'd be impossible to send a frame um, that's been broken up. So if you know you're always getting like one message, which can be many bytes, and it's important to know how many bytes are in there, then you probably want to use frame mode. Um, like I said, there's a little bit of overhead, but it's not much. You can look at it. It's basically just automatically handling, making the grants a little bit bigger, putting the header in there for you, and then when you read the grants back, getting the header, and then figuring out how many bytes to give you of that. So like it will automatically truncate the read to just the size of the frame. So it actually gets the full read, but then it shrinks it back to just the size of the frame and then gives you that. So it kind of transparently handles all of that for you. So I think that's pretty much all. So if you have any questions, now would be a really great time to ask them. But I think that's everything that I wanted to explain is basically like the four parts that make up BBQ. Like these four actions are everything that make up BBQ and how it works. How it acts kind of in normal operation where the parts just go round and round, and you can have as many like sub chunks in here. Like in these 128 bytes, you could have done that by getting two grants at a time. So this could have been 64 separate events. That's kind of why in chat I was talking about, well, it's not really broken up into two sections. You can break it up as much as you want, but the bipartite comes from like when these wraparounds happen. So like either when the producer wraps around and you go um from the end back around, or when the reader writes or the reader wraps when you go from the end back around. And the way that we achieve that is through those. I don't know if this was the page that had it on. But we do that by basically setting these watermarks, which allow us to kind of seamlessly swap those back and forth and prevent them in a thread safe way. What is the canonical pronunciation of your lib? I call it BBQ. So it's a play on barbecue and bit buffer Q. Barbecue just because I come from Kansas City and I think a lot about barbecue. But yeah, BBQ is too good of a pun to pass up. Now it's called like BB buffer because I reworked some stuff. I should probably just call it BBQ again, but what are you gonna do? But BBQ is probably how I would canonically pronounce it. If you want to call it barbecue, that's cool too. Um, is there something like a continuous buffer mode where old versions are overwritten gracefully? I know circular buffers do this sometimes. I'm not sure if it's um safe to do that. I don't I'd have to look. It could be possible. Like you wouldn't be able to write over something that already has a grant out because that would be undefined behavior. But you might be able to push the read. Well, no, maybe. Maybe the answer is maybe. It'd probably be kind of hard because I don't use like mutexes or locks anything. So this is all I've actually probably buried the lead on that a little bit. Is that BBQ um is also a lock free algorithm, which means there's no mutexes, there's no place that you like have to acquire a lock that could prevent you from being locked out. Um, it is a lock free algorithm. Trying the nice thing about the reader and the writer is you have like single responsibility where like the reader can look at where the writer is but doesn't write to where the writer is, and the writer can read where the reader is but it doesn't write to the reader. Like they each have one thing, and like the ordering of how you update those tracking variables is pretty dicey. You have to be really careful that you do it in the right order because otherwise you can end up making like overlapping grants, which would be really bad because that's immediately undefined behavior. I called it barbecue accidentally. Okay, yeah, BBQ is probably how I would pronounce it, but yeah. So to answer your question, weekend forever, it could maybe be possible. Definitely not if you already have a grant active, but if you don't have the grant active yet, then I could see it maybe being possible, but it might be really complicated to prove in a safe way. Um, Lock-free algorithms are famously tricky to get right and very easy to look like you got them right. And they work 99.99% of the time, but then they don't. A lot of this, like sitting down and mental modeling of whether my lock free algorithm was right, is Andrea Latituda from ETH Zurich. Like we sat down at Chaos Communication Congress a couple years back and just like sat down and drew out everything we could think of. And it still makes me sort of nervous whenever I touch the inside of that code. So if you actually look like all the versions of BBQ, the like core logic has almost always been exactly the same because I basically figured it out once and I don't want to touch it again because it makes me nervous. But yeah, it could be possible for a continuous buffer mode. Yeah, I would super appreciate a pull request or like just even thinking out what that would be like. But I don't plan on implementing that right now because usually I'm not doing something like that. But I know when you would want to do something like that. Like I said, if you have like your sampling accelerometers or something like that, and you always just want to overwrite the oldest data. But yeah, I don't plan to add that right now, but I'm sort of open to the idea if you could do it safely. Yeah, like I said, that's BBQ, what it is from a high level. How it's different than a regular circular buffer, how it's different from bit buffers, like traditional bit buffers, as well as ping pong or double buffers. Um, the four main building blocks that make it up, how it works in normal operation, how it works in producer wrapping, how it works in reader wrapping, and then also how the new framed mode works. So hopefully this is everything you wanted to know. I'll try and clean up these diagrams into much nicer diagrams and write a blog post, or maybe just a big PR to BBQ to add like, frame or not frame by frame, but like step by step with pictures of this happening. If there's anything that was particularly confusing, feel free to ping me on Twitter or in Matrix or something like that, or leave a comment here on the YouTube video. And I'll try and clean it up. But hopefully that was useful, and I hope everyone has a good Easter if you celebrate Easter. And if not, have a great weekend. And I will talk to you all soon. Thank you all very much.